So, in simple linear regression, we are interested in getting the distribution of the random variable, the dependent random variable y at different levels of x. So here in this figure, you can see that x equal to 0.2, x equal to x1 is a level, x equal to 0.4 is another level, and so on. So we have the different levels of x, and for those different levels of x, what do we notice about the distribution of y? We see that at the different levels of x, the distribution has exactly the same shape, which means the family of the distribution, which is normal in this case, does not change. So this is also a bell-shaped curve Gaussian distribution. This is also a bell-shaped Gaussian distribution at x equal to 4. At x equal to 6 also it's a bell-shaped curve, and so on. So family of distribution of y does not change. What else does not change with different levels of x? The variance, the spread of the distributions is also exactly the same, and scale of distribution of y, so family as well as the scale are constant, right? What is changing? The location parameter is changing, the mu, the expected value is changing, and that expected value at different levels of x is given by mu y conditional on x, right? This is also called conditional expectation, expected value of y given x. So this is conditional expectation, and this precisely is the definition of regression. So definition of regression. When someone asks you what do you mean by simple linear regression model, what does the word regression mean? Regression means nothing but the conditional expectation, expected value of y given x, which is also denoted by mu of y given x. And that is what is changing at different levels of x, x equal to 0.2, 0.4, 0.6, 0.8, and so on. These expected values are all connected along this straight line, right? So this straight line is actually the true regression line, also called the population regression line. So this regression line, each point along that line for different levels of x would give you the population expected value of y given x. So mu y given x denotes the population parameter. So this straight line here is called the true regression line, and we know that it is given by mu of y given x is equal to beta naught plus beta 1 times x. So it has an intercept term which is beta naught, and it has a slope term which is beta 1, right? So this green dot here represents mu of y given x equal to 0.2, and that value corresponds to 0.5. Similarly, somewhere here, somewhere between 0.5 and 1, you have mu of y given x equal to 0.4, and so on, right? So all these conditional expectations are given by the true regression line, which is given by beta naught plus beta 1 times x. Alright, so we have now sufficient background to formally define what is simple linear regression. Remember, our random variable y is a function of an independent variable x, and the relationship is a linear one in parameters. It's given by y equal to beta naught plus beta 1 times x plus some random noise, right? That random noise is white noise. It belongs to mean mu, mean 0. So the noise is white noise belonging to the normal distribution with mean 0 and variance sigma square. This model is called simple because it involves only one dependent variable and one independent variable. So the predictor x is a single predictor, right? That's why it's called a simple linear model, and it is linear because it is linear in parameters. Hence the name simple linear regression. Recall, what is the formal definition of regression? Regression is nothing but the conditional expectation. So the definition of simple linear regression is the conditional expectation expected value of y given x, which we have also denoted by mu of y given x. I had asked you to brush up your basic probability and statistics, and if you have brushed up, then you would recall that expected value, the definition of an expectation of a continuous random variable, is given by this expression, where little f of y is obviously the probability density function. So here f of y represents the continuous probability density function, right? And if this is the expected value of a random variable y, then you can extend this to the conditional expectation, which would be nothing but this probability density here would be replaced by the conditional density, which is f of y given x, right? Well, strictly speaking, if I have used the notation f here, I should write f of y given x, f sub y given x of y given x. This is how I should have written it in this expression. But loosely we drop this subscript y given x and we simply use the same f as the definition of a normal expectation. Strictly speaking, it's not so, but for all practical purposes we drop this subscript and use the same f. So this is what happens for a continuous random variable. If you have brushed up your basic statistics, then you would also remember that for a discrete distribution, let me use some other color. So for a discrete random variable, expected value of y would be given by summation over all the j's y sub j, the probability mass, probability of yj. So for a discrete random variable, instead of y taking any value along the real number, along continuous real numbers, y can take only discrete values. So p of y sub j would mean the probability that the random variable y is exactly equal to yj. So p of yj here would mean that the probability that y is exactly equal to yj. And those probabilities over all the j's, we multiply the probabilities with the values yj's to get the expected variable. So this is what the definition of expectation in general means, and therefore if you extrapolate it, you can write the conditional distribution as expected value of y given x would be equal to summation over all the j's, right, yj times the conditional probability that y is equal to yj given x equal to a certain level, which is xj. So this is how we would define the conditional expectation in case of a discrete random variable. So to summarize, in simple linear regression, y is given as beta naught plus beta 1 times x plus some white noise which belongs to the normal distribution with mean 0 and variance sigma square. This means that as the level of x changes, the conditional distribution y given x changes, but the family remains the same, which is normal distribution, and the variance remains constant. Sigma square is constant. So the change in the conditional distribution is only in mean. The family and variance remains unchanged. And the expected value of that conditional distribution is the conditional expectation mu y given x, which is given by beta naught plus beta 1 times x. Right? Now, therefore, simple linear regression has two parameters, beta naught and beta 1. Now, I want you here to pause for a second and think which of these parameters, beta naught or beta 1, would be physically more important for you. Remember, beta naught represents the intercept terms and beta 1 represent the slope term. So physically, this means that beta naught is the expected value of y, the mean value of y, if there were no x. So if there were no x, the expected value would remain constant, and that is nothing but the intercept term, beta naught. So what would be the mean value of y in absence of x? That would be given by the intercept term beta naught. Beta 1, on the other hand, indicates the change in the expected value of y per unit increase in x. So how mu y given x changes for unit change in x, that is what is physically represented by the parameter beta 1. And then therefore intuitively, out of beta naught and beta 1, more often than not, beta 1 is the parameter that is of more importance to you. Because if you remember our examples, let us take the sales versus advertisement. Advertisement expenditure is my independent variable x and the sales figure is y. And ultimately we are interested in testing whether if I spend more on advertisements by making Shah Rukh Khan endorsing the brand, am I going to increase the sale or not? So this question will be answered by the parameter beta 1. So in simple linear regression problems, more often than not, beta 1 is the more important parameter as compared to beta naught. And of course, the distribution itself, the conditional distribution, the conditional random variable y given x, that itself is normal. We know that the mean, the mu y given x, is beta naught plus beta 1 times x. So we can plug that in instead of mu y given x, and the variance sigma square, which remains constant. So the mean expected value is a function of x, whereas the variance is constant, homoscedastic. So this is the summary of simple linear regression.